So we've been discussing how to use the first derivative to find intervals where functions are increasing and decreasing. And once you can do that, we can locate extreme values of functions. So let's take a look at that in this video. When we talk about extreme values of functions, we're talking about y values. So places where y values are high and places where y values are low. Specifically, we're looking for maximums and minimums, because those are usually important places where functions can help us solve applications. And to be specific, there are two kinds of extreme values. There are relative extreme values, which are local, and then there are global extreme values, which are true for the entire function, the entire domain of the function. For this particular video, let's focus on relative extremes. So what do we mean by relative extremes, local extremes? Let's look at this picture here. You can see it depicts something called a relative maximum, and what that means is as long as we're looking at the neighborhood around that point, it's the highest one on the function. We're not sure what's happening other places in this function, but we do know that at around 5 years that there's a high point in this function. As you move along the x-axis, you'll notice we do have a low point down here. And again, if you focus in that red circle just on the area around that point, that dot is the lowest point. And so we call that a relative minimum. And then here again we have another high point. We call it a relative maximum. It's not really the highest point on that graph. There's lots of points that are higher over here. Right? There's all kinds of points over here that are higher. But in his little neighborhood, he's the top dog. It's kind of like a big fish in a small pond. So that's what we mean by relative extreme values. Functions, or excuse me, y values that are either the highest in their neighborhood or the lowest in their neighborhood. So just like we defined increasing and decreasing, we're going to define relative maximum. A function has a relative maximum at x equals c if there exists an open interval ab containing c such that f of x is less than or equal to f of c for all x in ab. And that's the way we describe in math language what I just talked about on the last slide. This guy right here is a relative maximum because all the other y values in the neighborhood are lower than that top one. Right here at x2, we have a relative minimum because all the other y values are higher than that lowest one right there. I'm going to talk about that on the other screen. I guess I'm supposed to focus on maximums on this screen. So there's another maximum. All the other y values near that top point are less. And here we are going to define a relative minimum, and that's what I was mentioning earlier. There's a relative minimum right here at x2 because, as I mentioned, all the other y values around it are higher. Same thing here. All the other y values are higher. These may not be the lowest y values of the function. It looks like there might be a lower one over here, but in their neighborhood they're the lowest. And again, we have this definition. For any point x equals c, it's a relative minimum if there exists an open interval around it, right, containing it, where f of x is always greater than or equal to f of c. The y values are always bigger when you're around it, except for that point. It's the lowest. So we're going to be using this fact to help us find these relative extreme values. And to do so, we're going to notice that something interesting happens to the derivative when we have a max or a min. In this first picture, letter A, we have a maximum here, and you'll notice that the derivative is positive for points on the left-hand side of that point, and it's negative for points on the right-hand side. The slope changes from positive to negative where there's a max. Similarly, the slope changes from negative to positive where there's a min. And so we can use that to help us find these extreme values. The trick is to locate those critical points that I mentioned in the previous video. the changes in sign of the first derivative can only occur at one of those special points. And the critical points, remember, are places where the first derivative equals 0 or where it doesn't exist, where it's undefined. So if we go hunting for those points, those are the only possible candidates for these extreme values, and we just have to check those out. So here's a diagram that shows some types of critical points. When the first derivative is 0, we have horizontal tangent lines. So a lot of these critical points have horizontal tangents. But we also have points where the derivative is undefined, these corner points or cusps, and also vertical tangents or asymptotes. So these are all considered critical points. You'll notice that some critical points do not provide us extreme values. There is a horizontal tangent here at 0, but this is not a high point or low point. It's just an interesting point there in the middle, and we're going to talk more about those in a later video. So how do we find these extreme values? Well, we're going to use the first derivative test. And it's outlined on page 54. I know it's hard to read here, but you can refer to that. And basically, this tells us that we're going to determine the critical points. We're going to make the sign diagram, and then any place that changes from positive to negative, that's going to be a relative maximum, and anything that changes from negative to positive is a relative minimum. The first derivative can't help us if the signs don't change. So if it goes from negative to negative or positive to positive, those are not extreme values. Here's a summary of that first derivative test that's a little easier to read. We're going to get the critical points. We're going to make that sign diagram. If the sign diagram goes from minus to plus, we have a minimum, and that's because, remember, the minus means we're decreasing, and the plus means we're increasing, so that's a minimum. And if we go from plus to minus, we're going to have a maximum, because that means increasing to decreasing, so there's a high point. And then to get the extreme values themselves, we plug in the x values of these relative maxes and mins into the function to figure out how high or how low they are, to get the y value. So let's revisit those examples from the last video. For f of x equals x squared, the sign diagram, remember we had a critical point at 0. It looks like this. It's negative, right, decreasing on negative infinity to 0, and increasing on 0 to infinity. So we have decreasing to increasing. So this is a minimum. Now to find out what that minimum value is, we simply plug that back into the function. F of 0 is also 0. So we have a relative minimum at 0, 0. And here you can see from the graph of f of x that that's absolutely true, right? Here's our 0, 0. It's certainly a relative minimum. In fact, we're going to find out later this is called an absolute minimum because it is the lowest y value for the entire domain of the function. So we had a very similar sign diagram for f of x equals x to the 2/3. Our critical point was 0. You may recall that we had f prime of x equal to 2 over 3 cube root of x. The only critical point is 0 because the derivative is undefined there. And we did a sign diagram and we found out when you plugged in negative numbers, you have a negative derivative, so we're decreasing. When you plug in positive numbers, you have a positive derivative, so we're increasing. And since 0 is defined in our function, we do have a minimum here. And remember, we're not going to plug it back into this derivative. We're going to plug it into this function here. When you plug in 0 into x to the 2/3, you do get 0. So this point is again 0, 0. Different function, but it has the same relative minimum. Let's take a look at the graph just to verify. And as we expected, you can see we do have a minimum value here. That derivative is undefined. It's a cusp there. That is a critical point. It is a relative minimum. And like I mentioned for the other function, this turns out to be an absolute minimum as well, because that's the lowest point for all the values of this function. Here's that cubic that we worked with. The sign diagram for this was a little more complicated. If you want to see the work for how we made the sign diagram, you're going to have to watch the other video. Sorry about that. I'm trying to make this as brief as possible. We had critical points at -2 and at 4. And it turned out to look like this. We were positive, so we were increasing over here. Then we were negative, so we were decreasing. And finally we were positive again, so we were increasing. When you go from positive to negative, from increasing to decreasing, you have a maximum, a relative max. And when you go from decreasing to increasing, you know we have a relative min. And to find those function values, we're going to plug the values back into the function and figure out the y values. Now I've done some calculations, and when you plug -2 into this function, you get a value of 60. So our maximum is going to be at -260, our relative maximum. And for our minimum, when we plug in 4 to our function, we get -48. Let's find out from the graph if we're correct. So here's our graph of our function, and sure enough, here we have -260, and that's a relative maximum. And down here, I think you'll agree that this is 4, -48, right about there on the y-axis. These are both relative extreme values, because 60 is not the highest value that this function attains. These guys up here keep going forever. Same thing with -48. The function down here actually goes lower, but in the neighborhood of -2, -260 is the highest point, and in the neighborhood of 4, there's -2 in the neighborhood of 4, -48 is the lowest point. Finally, let's revisit that function, x plus 1 over x. Our sign diagram, I guess I'll make this one, let me erase that. Our sign diagram had 3 critical points, -1, 0, and 1. So we had 4 intervals to look at. We found out that it was increasing on 2 intervals, from -infinity to -1, and from 1 to positive infinity. And we found out that it was decreasing from -1 to 0 and from 0 to 1. And remember, there's an asymptote at 0 because that function is undefined at 0. It's not even part of the domain. So what that tells us is we have a max, relative max, at -1 and a relative min at 1. And the way we figure out those values is plug it in. So when I plug in -1, I get -1 plus -1, which is -2. So this is -1 comma -2 for the maximum, relative maximum. And when I plug in 1, I get 1 plus 1, which is 2. So that minimum is 1 comma 2. Notice the maximum is actually lower on the y-axis than the minimum is. But remember that asymptote came into play in this graph. So let's take a look and see if we were right. And you probably remember from the other video that this graph has an interesting characteristic in that it has an asymptote here, and on the left side it's going to infinity, and on the right side it's going to positive infinity. And here is our local maximum at -1, -2, and here's that local minimum or relative minimum at 1 comma 2. And you'll notice our max is actually lower than our min, which is interesting. But that's possible because there's a jump in this graph. So hopefully this has given you an introduction to using that first derivative test to find these extreme values. Get the critical points, break up your interval, make a sign diagram, and then interpret the sign diagram to find your maximum values. Good luck.